Welcome to the final Crescendo General Assembly, which is going to be just a scientific conference. And to remind people that a deliverable of Crescendo will be the presentations in a PDF form, plus the abstracts you've produced. Hazel has asked me to remind you to mute your microphones if you're not speaking. And also, if you have any questions, please type them into the chat. And then if there's time, I will pose them to the presenter. If not, maybe they can pick them up afterwards offline. So each talk has 10 minutes plus 2 minutes for questions. And I think, Hazel, you will give them a 2-minute warning when there are 8 minutes. Is that correct?
Yeah, that's right.
Yep, right. Okay, and we will record everything. So we'll use this on the Crescendo website. So if people have any problems with some of their stuff that they don't want to be shown, please let Hazel know as well. Okay, so without further ado, I suggest we get cracking. So we have 7 talks coming up now. We will, obviously we're a couple of minutes late starting, but we will run over by 1 or 2 minutes in the first session. But first up is Kat Scott from the University of Leeds. Kat, are you able to share your screen? Okay, and over to you, Kat. Make sure you unmute yourself.
Yeah, always got to remember to do these things in the right order. Yeah, morning everyone. Thanks so much for the chance to present this work this morning. It's a shame, obviously, we haven't had a chance to meet up in person again at the end of the project, but it's good to have this opportunity to catch up with everyone online. So I'm going to be talking about the representation of biogenic secondary organic aerosol in the Crescendo Earth system models. I've listed here a lot of the other people who are involved in work packages 3 and 6 that have gone into this work. So thank you very much to all of them. So you'll be hearing later on this morning from some of the other members of these work packages who have been looking at different natural aerosols. I'm focusing on biogenic secondary organic aerosol, which is formed in the atmosphere because of the emission of biogenic volatile organic compounds from vegetation. So in terms of getting that right in Earth system models, there are a number of different stages that we need to try and represent. So really the key parts are in terms of how the 5 Earth system models that we're looking at as part of Crescendo, they kind of fall into two main categories that either simulate the gas phase part of this process, so the emission of the VOCs and their subsequent oxidation. So the 3 models at the bottom here, NORI-ESM, UK ESM and EC Earth simulate the gas phase and then the oxidation of the VOCs to form SOA. And the 2 models at the top, CNRM and IPSL, are treating the SOA in the particle phase straight away. And then there are a couple of other details about the way that the different models represent SOA. So NORI-ESM and UK ESM, we are running them with an interactive land surface, which means that the vegetation in the model is actually generating its own volatile organic compounds. And that's important, and that's what I'm demonstrating here. So this graph on the left-hand side, I'm just showing a couple of years as an example, the global total emission of monoterpenes, which are a type of BVOC. And you can see that the kind of purple colours and the green colours for NORI-ESM and UK ESM, there's a little bit of variability year on year in the amount of these BVOCs that are being emitted. But the other point I want to make is that you can also see when you look at the NORI-ESM versus UK ESM bars in particular, that there's quite a big difference in terms of the different biomes that these emissions are coming from. So in NORI-ESM, the majority of the emissions are coming from the tropical latitudes, whereas it's a lower proportion in UK ESM. And then in EC Earth, there are gas phase BVOCs, but they are not being generated interactively. So that's why that line is constant for all those years. So as I mentioned at the start, there's kind of various kind of cogs in the process of trying to get biogenic SOA simulated accurately in our models. And I'm just going to show a couple of highlights from the analysis. So I'm at the point of writing this up, writing the whole analysis up, but I'm just going to show a couple of things here. So one thing is that organic aerosol is pretty much everywhere in the atmosphere. So to look at biogenic secondary organic aerosol, we really have to find locations where we expect to see a strong contribution from this natural aerosol source. And so what this plot is showing us is the seasonal cycle in the amount of organic aerosol mass at a boreal forest site in Finland. So you can see that the observations in black show a really strong seasonal cycle with a summertime peak of organic aerosol mass. And you can also see that the models broadly are capturing this peak in the summertime. Some of the models, so EC Earth, for example, has higher concentrations during the winter than we would expect, but that's not likely to be a natural, as a result of natural processes. So broadly, they're doing a good job at getting this seasonal cycle. And when we have a look in more detail at, for example, here, NORI-SM in one particular year, we can, with NORI-SM, we can extract the amount of SOA that's coming from, that is SOA, so the secondary biogenic stuff, and then the primary organic aerosol. And we can see from this that it's really, really strongly that it is the secondary organic aerosol that's capturing this summertime peak. And actually there might not be enough of the primary aerosol represented in the brown shading. That might be why we're getting underestimates during the winter. So we've looked at this at other locations, but I'm just showing a couple of particular comparisons here. So it's useful to compare what the models are doing to very specific locations and times and try and get the models to reproduce what we see. But what we really want to know is whether the Earth system models, when we run them into the future, are going to be able to capture the changes that we expect to see. So BVOCs, their emission is strongly controlled by the climate, temperature in particular. So we know that the emissions are controlled by temperature in the models. The emission parameterization will reflect that. So we know that the emissions will increase when the temperatures are higher in the model. But what we want to know is whether that feeds through to give us an increase or otherwise in the amount of organic aerosol that's simulated, and how that relates to what is observed in reality. So again, choosing our favourite Finnish boreal forest to look at, what this plot is showing on the left-hand side is the relationship between air temperature at the surface and the amount of organic mass that's simulated in the models, and then observed at this boreal site. The black crosses are the observations. So what we can see from this is that when you take time kind of out of it, we're just looking at how the composition of the atmosphere varies with temperature. We can see that there does tend to be more organic aerosol in the air when the temperatures are higher. And what we can see when we look at the model responses is that the models all capture this positive relationship, but it's actually only NORI-SM and UK ESM who have the interactive land surface models generating their own biogenic VOC emissions that are able to capture the strength. So what I'm showing in this table on the right hand side, the gradient here, the gradient of the lines in the plot basically represents the amount of enhancement in organic aerosol mass you get per degree of warming. So this is very positive. Again, with some of the models, we were able to dig into this a little bit further. So in the models that track the amount of primary organic aerosol and secondary organic aerosol separately, so not all models do that, but in NORI-SM and EC Earth, we can break down the organic aerosol into those primary and secondary components. And so on this plot on the left-hand side, I'm showing the same thing here. It's the relationship between organic aerosol mass and temperature, but broken down into the primary or the non-SOA bit in the solid symbols in the circles and the triangles, and then the crosses are the secondary organic component. So what we can see from this really clearly is that for NORI-SM, which has got the interactive BVOC emissions driven by the land surface model, this secondary organic component is capturing the strength of that relationship between observed organic mass and temperature.
2 minutes.
Real, thanks Hazel. The primary component isn't doing that. We wouldn't expect it to. But we can also see from this that when we look at EC Earth, which also separates out the primary and the secondary aerosol, we can see that we don't see that same relationship being captured. And that's because the emissions of biogenic volatile organic compounds are not being driven by temperature changes in this model. They're fixed every year. So this is a really nice demonstration of the value really of having that interactive VOC emissions in the model in terms of getting the ultimate atmospheric composition, simulating that correctly. Again, this is just one location, so I'm trying to find more places where we've got a long enough observational record to pull out this relationship with temperature, because that's not, it's actually quite rare to find locations where we have this detailed composition information in terms of the aerosol. So that's all about aerosol composition, and I'm just going to finish by saying what I would also like to do, and what I'm working on at the moment, is to revisit some analysis we did before, looking at the concentration of particles in the atmosphere that are bigger than 100 nanometers. So this is the kind of particles that could be potentially acting as cloud condensation nuclei. And again, we have seen that there's a positive relationship between the number of those particles and temperature. And this is just on the right-hand side, this is an example from our offline aerosol model, GLOMAP, which is part of UK ESM. And so I want to see now whether the Earth system models are able to capture this relationship between temperature and particle number, as well as the aerosol mass, because it's notoriously quite difficult to get aerosol mass and number behaving in both behaving well compared to observations. So I think that's my 10 minutes. So I will just finish there by saying that we've seen that the models are broadly able to reproduce the seasonal cycle at boreal locations. And I didn't show the results from the Amazon, but they tend to over-predict the amount of aerosol we see, organic aerosol we see there. And then promisingly, they are able to capture this positive relationship between temperature and organic aerosol. But really, it's the interactivity of the BVOC emissions is key. And now we're going to be looking at aerosol number and how that affects things. So thank you very much.
Okay, thank you, Kat. And there are two quick comments / questions, so I'll quickly read them out. Bill Collins, BVOC increases cause the largest aerosol feedback in the CNIP6 models. It seems from your talk you think this is a robust feature in the models. Would you like to comment on that, Kat?
Yeah, I mean, so I guess that's the key issue, isn't it? That the models are driving the aerosol feedback in terms of radiative effects is going to be the impact on number and therefore cloud forcing. So I think this next stage of the comparison, where we're looking at the number concentrations, is hopefully really going to help us to dig down into why, helping to explain the differences between different models and their aerosol feedback.
Okay, quick next one from Victor. Is there a geographical difference in temperature dependence between tropical and boreal forests?
That is something that we would like to know. So I'm compiling from the tropics, but we just don't tend to have until quite recently, there hasn't been really a long enough time record to try and do that kind of analysis. So they've been doing it for a long time in Finland, but that is really what we'd like to know, because of course that is where most of the SOA is. Okay,
and there's one more question about the forcing of the feedback from Peter in the chat. I wonder if you could answer that one offline, so we'll have to move on now.
Yep, sure.
Check the chat. Thanks very much, Kat. Okay, next is Fiona. If you'd like to share your screen, Fiona. Kat, and share maybe.
I had difficulty sharing my screen, so hopefully Hazel is going to show my PDF. Thanks, Hazel.
Okay, off you go then, Fiona.
Thank you, Colin. Good morning, everyone, and thank you for the opportunity to present some work that we've done on understanding the present-day forcing of methane. Next slide. So part of the motivation behind this work is, next slide, Hazel, please. Part of the motivation behind this work is really to better characterize how changes in anthropogenic activity are impacting on climate forcing, and we're addressing some of the shortcomings in the 5th assessment report by using a preferred metric of choice, the effective radiative forcing. And we also have the advantage of coordinated experiments within 2 MIPs, the radiative forcing MIP and AirChem MIP. So the ERF is diagnosed from 2 model simulations using the same sea surface temperatures, where a perturbation has been applied to one of the experiments relative to a control. And in this case, it's a methane concentration perturbation. And then the ERF is diagnosed as the global mean time mean difference in the top of atmosphere radiative fluxes. Next slide. So another motivation for this work is the analysis by Ginny Thornhill that was funded by Crescendo and was published earlier this year. Using radiative kernels, she split the ERF, represented here in blue, from the AirChem MIP models that have run this methane experiment into its stratospherically adjusted radiative forcing represented in the grey bars, and then some of the tropospheric adjustments which are now included in the ERF definition. And the sum of those tropospheric adjustments is shown here in orange. As you can see, all of the models except UKESM1 have tropospheric adjustments which are negative. However, in UKESM1, the sum of the tropospheric adjustments are positive, which is largely due to a positive cloud adjustment. So the aim of this work really is to provide a process-based understanding of this positive cloud adjustment. Next slide. So here we look at the breakdown of the ERF into its clear sky and cloud radiative effect components using the recommended method by Stephen Gahn. So the clear sky components here are including a potential contribution from the aerosol instantaneous radiative forcing, or an aerosol forcing due to aerosol radiation interactions. So although the bulk of the methane ERF is in the clear sky components, particularly the long wave, we do see a positive change in the cloud radiative effect, consistent with Gillian's kernel analysis, and we see that the positive shortwave cloud radiative effect is outweighing the negative change in the long wave. So by using additional paired simulations with UKESM1, we've been able to see that the cloud radiative effect is only positive when aerosol cloud interactions are active. So when we disable the aerosol cloud interactions, as you can see in the bottom row of the second table there, the sign of the cloud radiative effect switches from positive to negative. And so when aerosol cloud interactions are disabled in UKESM1, the change in the cloud radiative effect is now more consistent with the other AirChem models. So the question is, why do we have this positive cloud adjustment, and what's driving it? So let's look at secondary aerosol formation in UKESM1 with a focus on both sulfate and secondary organic aerosol. And Kat has given us a nice introduction to secondary organic aerosol in the previous presentation. So moving to the next slide, here we're looking at the sulfate aerosol budget. And we find that the secondary formation of sulfate aerosol on a global annual mean basis is unchanged as a result of the methane perturbation. However, we see that the pathway to that aerosol production does alter as a result of methane-driven changes in oxidants. In particular, if you look at the schematic, we're producing sulfate aerosol through the oxidation of SO2 via 3 oxidation pathways, only one of which is in the gas phase, oxidation by OH. And that's the only pathway that leads to new particle formation in UKESM1. And we see that the amount of SO2 oxidized through that pathway is reduced by about 14%. And you can see here the unstippled areas here showing the statistical significance of that difference at the 95% level. So it means that our sulfate aerosol production, although is the same in terms of global totals, as a result of the methane perturbation, we are getting less production of sulfuric acid in the gas phase, less new particle formation, and a change in the aerosol size distribution. Next slide. If we look at the influence of the biogenic secondary organic aerosol, again, we've done a global budget, and you can see that the main terms of the organic aerosol budget remain unchanged as a result of the methane perturbation. However, we do alter the relative contributions of the different oxidation pathways of monoterpenes. And that oxidation is producing an oxygenated VOC of low volatility, which then solely condenses onto the pre-existing aerosol. So there's no new particle formation of biogenic SOA in UK ESM1. So the sulfate-driven change in the aerosol size distribution is modulated by the condensation of this volatile organic onto the pre-existing aerosol. So the global mean SOA production remains unchanged, but we do see less condensation onto the nucleation and Aitken soluble modes, which has been driven by the change in nucleation as a result of changing oxidants. Moving on to the next slide, if we look then at the aerosol response, we can see if we look at AOD, there are regional changes in aerosol optical depth, but on a global annual mean basis, these are near zero. And so actually there's no aerosol forcing from the methane experiment due to aerosol radiation interactions. And you can see, looking at the size distribution, we see statistically significant reductions in Aitken mode number concentration and accumulation mode number concentration. So this then on the next slide feeds into reductions in cloud droplet number concentration, showed here in the middle panel on the top. And we actually see a reduction in overall cloud fraction, both in low cloud and in high cloud. And you can see those reductions in cloud fraction are spatially correlated with those regions that show a positive net cloud radiative effect, which, as we've said before, is the balance, is where the positive shortwave cloud radiative effect is outweighing the negative. We see little evidence that the positive cloud adjustment is dynamically driven, so it does appear to be solely attributable to chemistry aerosol cloud interactions, with the positive shortwave cloud radiative effect outweighing the negative in the long wave.
2 minutes.
So moving on to my final slide then, thank you Hazel. We find that the methane ERF from UK ESM1 is one of the highest forcing estimates of the AirChem MIP models. Part of that high value is due to the inclusion of tropospheric chemistry, and so there's an indirect effect from methane driven changes in ozone, and that's consistent with other AirChem MIP models. However, part of it is also due to a positive cloud adjustment, making the sum of our tropospheric adjustments in UK ESM1 positive, and that is inconsistent with the other AirChem MIP models. So looking at the aerosol budget in more detail and looking at the cloud responses, we see little evidence that that positive cloud adjustment is dynamically driven. It's rather more of an aerosol mediated cloud adjustment, which is driven due to changes in oxidants, altering the production pathways of sulfate aerosol in particular, giving rise to a change in the size distribution. And so we see a reduction in the availability of cloud condensation nuclei, a subsequent reduction in cloud droplet number concentration, and then there's an overall reduction in cloud fraction, giving rise to a positive shortwave cloud radiative effect dominating over the negative change in the long wave. Thank you very much.
Okay, thank you, Fiona. Question from Bill. Is there a structural reason why the other crescendo models don't show an effect of methane on CDNC from sulfate?
That's a good question, Bill, and I'm not sure I've quite got to the answer yet. We know from Kat Scott's presentation, for example, that the biogenic VOCs do give rise to new particle formation in two of the crescendo models, NOR-ESM and EC Earth, and that isn't the case in UK ESM1. So it does appear that we have a strong sensitivity to that SO2OH oxidation pathway and the subsequent nucleation. And it may be that if we had other mechanisms for new particle formation, like boundary layer nucleation or a biogenic mediated nucleation, that we may be less sensitive then to those oxidant changes. But I'm not quite there yet in really understanding why that's the case.
Okay, and I think you've answered the question I was going to ask, but I'll ask it in another way. So the cloud response that you see, that seems to be somewhat unique to UKSM1. I think you were just talking about that, but are other models not having that because they lack the processes that are there, or they have more process pathways?
I have to look back on Gillian's paper in more detail. I think there were a couple of other models that had a very small positive cloud adjustment, but it wasn't sufficiently positive to make the sum of all the tropospheric adjustments positive. Okay. In the case of UK ESM1, the cloud adjustment is strongly positive, result and offsetting those other tropospheric adjustments. So there are other models that have two-moment aerosol schemes, and yet they're not giving the same response. So initially I thought it was because our model was a two-moment aerosol scheme, but it's not the only model that has a two-moment scheme, whereas we might expect a mass-based aerosol scheme to show differences. So again, not fully aware of the reasons why, but certainly something we ought to look into. But okay. It does seem that UK ESM1 is overly sensitive.
All right, thank you, Fiona. We have to move on.
Thank you.
Thank you. Next is Thomas. If you'd like to share your screen, Thomas.
Certainly trying to. Here we go.
Yep, that looks good. You're up. Okay. And away you go, Thomas, all yours.
So, good morning, everyone. I'm going to take you on a little trip through time, and I'm going to cover a few timescales that you don't usually touch upon in Crescendo. What I'm presenting today actually arose out of the PELMOD, the German paleomodeling project. So it's not actually part of Crescendo, but it touches upon quite a few of Crescendo's issues. So methane in the climate system. What's actually interesting about that? So this is ice core data from the LGM to pre-industrial, and first of all, what we see is that the range, that the changes in methane are actually quite substantial during the between the glacial and the interglacial. So we have roughly a doubling of methane between the LGM and the early Holocene. Then during the mid-Holocene, we have a dip of about 100 ppb, so that's also quite substantial. And what we also see is that we have these rather quick fluctuations. Actually, sometimes we have substantial changes between two samples in the ice core. So these changes are about 150 ppb from the Berling-Ullerud into the Younger Dryas and back again into the early Holocene. So obviously we want to understand why the climate system leads to these very large and fast fluctuations in atmospheric methane. Now, on the other hand, if we look at the more recent times, we see that methane has actually doubled since pre-industrial times. And the obvious question is how this will continue. And as we have a very fast climate model, we decided to also look into the future methane evolution. So we're using MPI ESM in version 1.2. So this is basically the CMIP6 version of the Max Planck Institute Earth System model. But we do have a few extensions that are not quite standard. So we're starting with an adaptive land sea mask and adaptive glacier mask, adaptive river routing, as over these timescales we have quite substantial changes in orography. Then we obviously need a methane component, so we have a wetland methane module with a top model based wetland estimation algorithm. Then we have modules for fire methane emissions, termite methane emissions, and for the soil methane uptake. What we're still missing are methane from ruminants. So if anybody can tell me how to model ruminants under glacial conditions, I'd be very happy to talk to you. And we're obviously also missing geological sources, which we have to prescribe. And we also have a atmospheric sink component, which our colleagues in Mainz developed for us. This is obviously not a fully fledged atmospheric chemistry model, but rather a very reduced formulation of methane chemistry. Finally, what I'm showing are coarse resolution experiments in T31 resolution, so that's roughly 3.75 degrees. We are not actually running the oceanic carbon cycle component. We are prescribing orbit and greenhouse gases and ice sheet, even though we are right now developing a version that is fully coupled to an ice sheet model as well. And what I'm showing are transient experiments from 25 kiloyears before present to the future. So, past atmospheric methane. What you see here is in black the ice core data, in blue is what the model tells us. What we see is that we do get the transition from last glacial maximum to early Holocene, and for that matter pre-industrial, more or less all right. It's not quite perfect, so we still need to deal with a few issues here. What we obviously don't get are these rapid fluctuations at the Berling-Allerød and going into the Younger Dryas. And well, that is actually due to the fact that we get an MOC shutdown as soon as we start getting into the Berling-Allerød. So the AMOC very much determines the behavior of atmospheric methane on these timescales. And if we do an appropriate MOC perturbation experiment, you see we can actually reproduce the ice core data rather well. Most of this is actually driven by the net land methane emissions. And these are pretty well constrained actually, because they're very much determined by the changes in soil carbon and atmospheric carbon dioxide. So these two components determine roughly 80% of the change in methane emissions between last glacial and pre-industrial. So the exact extent of wetlands and so on and so forth doesn't play as much of a role as one might think. However, we're still troubled by our inability to actually get the mid-Holocene decrease in methane concentration. We just don't understand why, what is happening there, or rather what is not happening there in MPI ESM. Anyway, so this was a little excursion into the past. So let's look into the more recent past and the future. So obviously we need to add anthropogenic emissions to our model there, and obviously we cannot simulate them interactively, so we need to prescribe them. And what I'm showing here is the historical anthropogenic emission data on methane. Actually, so the period from 1970 to 2014 seems to be known relatively well. At least it was part in the official CMIP6 data release. However, the period from 1850 to 1970 apparently isn't known all that well. At least it wasn't part of the official release. It's only available as a supplementary from Hoseley, whereas every other trace gas is available from 1850 onwards in the official release. And before that, we do a linear interpolation from 0 just to fill all the gaps. And for the future, we get anthropogenic methane emissions from 5 SSP scenarios, so from 119, 126, 245, 370, and 585. And as you can see, 370 is basically the highest methane emission scenarios where anthropogenic emissions reach nearly 800 teragrams of methane per year. Afterwards, the scenarios end in 2100, and afterwards we do a linear interpolation to 0, again, just to fill all the gaps. When it comes to the other greenhouse gases, we're using the Mainshausen and also the CMIP6 forcing data until 2500, and after 2500, we're keeping N2O constant while we are obtaining a CO2 trajectory from the Climber 2 EMIC, which was basically fitted towards the Mainshausen data until 2500.
2 minutes.
Okay, and this is what we get for future methane. So the natural net methane emissions increase by a factor of 4 in the high global warming scenarios. So natural emissions become larger than the anthropogenic emissions in nearly all of the scenarios where warming becomes larger than 2.6 watts per square meter. This leads to atmospheric concentrations which are substantially higher than in the Mainshausen et al. Scenarios. And this is simply due to the fact that Mainshausen assumed constant emissions after 2015, or I should say constant natural emissions after 2015, which is obviously not appropriate if we take the model natural methane, the changes in natural methane emissions into account. So I think I've shown that we cover the natural methane cycle decently for the glacial climate, so we can, the wetland emissions are largely determined by changes in soil carbon and atmospheric carbon dioxide. We get the Berling-Allerud-Younger dryas transitions if we have an appropriate MOC perturbation. The atmospheric sink is not quite as mature as the emissions side of this, so we still need some work on that. In the future, our model shows that atmospheric methane will increase strongly in warm climate states, and natural emissions become larger than anthropogenic emissions in all scenarios where the forcing becomes larger than 2.6 watts per square meter. Therefore, the CMIP6 scenarios severely underestimate the natural emissions and thus the future methane concentrations. And finally, the methane will stay quite large, the concentration will stay quite high for as long as climate stays warm. So thanks very much for listening.
Thank you, Thomas. I'll start with a question, because early on you sort of said that that AMOC controlled the sudden drop in methane as though that was a common knowledge to everyone, but it's not common knowledge to me. So could you explain what the mechanism is there that AMOC's playing a role?
Basically, it's subtropical wetlands which drive methane during that period. So it's tropical and subtropical wetlands, and those are largely situated around the Atlantic Ocean. So we have substantial wetlands in northern Africa at the time, which may come to a surprise to a few of you. However, we do get quite a green Sahara in MPI ESM, and that is one of the sites where a lot of methane comes from at that time. And if we have a shutdown of the AMOC, we get obviously a cooling in that area and therefore a reduction in methane emissions.
Okay, understood. And the factor 4 increase in natural emissions going into the future, are there other models that have done similar experiments? And can you comment on whether MPI, if that's a ballpark figure, or it's high compared to other models or low compared to other models?
Actually, this is a somewhat difficult question, because all of the experiments that I've seen end in 2100, and the interesting period is 2100 to 2300. That's where the real increase happens. So the increase to 2100 is slightly higher than in some of the other model results that I've seen, but it's not completely outrageous.
Okay, all right, thanks very much. Then we're going to move on, and next up is Yves. So if Thomas could stop sharing and Yves could share.
Yeah, can you hear me?
I can hear you very well, Yves. Yep. Welcome.
Okay, perfect. You can see the
and
screen.
you're on screen. Off you go.
So I've done a slight modification to my title because Jim Haywood pointed out to us that you don't necessarily get to an improvement of ESM tropical precipitation by taking into account dust absorption, and I will show you that a little further down the talk. First, I'm going to show you how accounting for aerosol property, dust properties, changes tropical precipitation in models. And when you look more specifically at African monsoon, it's the advection of water vapors that matters. So it's this channeling of energy through the tropics that you see here in this graph, which comes from very small term in the net energy budget. And you have a north to south advection in the atmosphere and a northward advection of the energy in the ocean. If you look at experiments that have been done in the past, looking at how you could improve this transfer of energy at the equator, you have here the CRES net energy that's shown for the atmosphere in red, for the ocean in blue, and the total in black. And these are experiments done by Jim Haywood, where he varied either the stratospheric aerosol, adding stratospheric aerosol, either change the ocean albedo, or either changing cloud microphysics. And he showed that he could improve the energy transfer from northwards at the equator by a combination of these experiments. Here, what I will be doing by accounting for dust absorption is playing on the same effect. So what set us into this is that there were experiments that had been done mostly by Ron Miller, but also by Fabian Salmon, and in the group of Natalie Mahowal by Oshoka, that showed that you could really change the precipitation over the Sahel by increasing the absorption. There were other effects of interest, such as a change in the African easterly jet caused by dust, or also explaining long wave radiation anomaly. And here what we have done is to, from observation, to estimate from the dust mineralogy, and that's the original part of this work, is really to start from dust mineralogy and how much you increase the absorption in the short wave by accounting correctly for iron oxide content. Another effect comes from accounting for large particles, which few models do, particles between 10 and 100 micron, which are difficult to model. And I want to point out that there was a paper by Stephanie Fiedler coming out recently that say that these ESM really have been struggling in the last 15 years to improve tropical precipitation. First, from the observation, what I show you here is the main absorber from dust is the iron oxide, and Sahel has quite a bit of iron oxide. That's got us interested. So roughly you have about 3% content of iron oxide over the Sahel. This comes from maps that we built with Tanguy Kleinen, Michael Schulz in 1999 and work by Nikovic following that work. The second set of very interesting measurements come from Claire Ryder during the FENEC and the ARD campaign. Here on the x-axis, I show you increase of absorption from the right to the left. So here you have a single scattering albedo of a non-absorbing aerosol, and the more you will go in this direction, the more you absorb shortwave radiation. And you see that as you increase the effective diameter of the dust, you increase considerably the absorption by quite a bit. And about here, you go from a negative top of the atmosphere net to a positive one. Another graph that's interesting in this paper of Claire is the error you make by not accounting by large particles in terms of difference in single scattering albedo of 550 nanometers. So you see that you have quite important errors that go from 0.02 to 0.10 in single scattering albedo, which is considerable. So what we set out to do was to take an optical model that accounted for the main minerals of dust. And what I represent here is how the absorption here, so the absorption increases from left to right this time. Oops. Absorption increases from left to right because I represent 1 minus the albedo, the co-albedo. And here I varied the iron oxides in my model from 1.5% content to 10%. So the blue line corresponds to when you account for only small particles of less than 10 microns. And the orange line is when you account for particles between 10 and 100 microns, sorry. So you see you have quite a shift by accounting for larger particles. And you also have this shift as you increase the iron oxide. It's interesting to notice that for 5% content of iron oxide for 10 micron particles, or less than 10, is equivalent to a 3% iron oxide content when you consider the whole size distribution, observed size distribution for the aerosol. Also represented here are measurements in blue during the ARD campaign, so it ranged from 0.01 to 0.09, and in light pink from 0.02 to 0.14 is a Fennec campaign. And the case we retain for Sahel is this case with 3% iron oxide here. So here I show you what I just represented in the graphic. I took the 5% case and the 3% case, and I show you that over Sahel, have a considerable absorption. You have about a 17 watt per square meter absorption, and these two cases are really equivalent. You have a net of about 5 plus 5 because it's heating over the Sahel. The short wave is considerably reduced at the surface by 11 watt per square meters, and your absorption is the difference between the two is 17 watts. Here is a representation of what's happening. So we studied this region over the Sahel. This is the values for Sahel between 10 and 20 north and between 15 west and 35 east. This is where we'll show you the results. And to really see the effect on precipitation, you have to use a full-blown fully coupled model. And we ran for 100 years, and we analyzed the last 30 years from 1915 or 2014. And from now on, I will show you differences between the simulation with dust, absorbing like over the Sahel, and the simulation without dust.
2 minutes.
Thanks. So this is a difference in precipitation. You see a considerable increase during the summer months from June to September of 0.5 millimeter per day here. And in all models, I don't show you the other models, but other models that have done the experiment, you see a decrease in precipitation over the Amazonia, which is quite interesting. Here is a half molar diagram with the trim observations here that show you how the precipitation migrates north from 5 south to 15 north. And you see that the migration, at least in the IPS LCMC model, is much better represented with the dust than without dust. Here is the difference between the two cases that show you the increase in precipitation at latitudes of about 10 degrees north in the summer months. And this is my last transparent of results, and maybe the most important one. We show you the bias. This is a line for the Sahel. We had a bias of minus 1.2 that we reduced considerably by about 30%, and with an increase in precipitation of 20% in the summer months. We also improved the correlation, but it's not only true over the Sahel, we also improve things over North Atlantic and West Indian Ocean, which is more difficult to understand, without having a significant degradation in other regions of the world. So this is a map of what's happening with the advection of water vapor. And what I tried to summarize the result here, that when you account for the strong absorption of dust over the Sahel. And when you also account for very large particle, which has not been done before, you, at least in the IPSL CM6 model, you improve precipitation over these three regions that are the Sahel, tropical North Atlantic, and the Western Indian Ocean. And this improvement is more triggered by thermodynamics rather than variation in the tropical circulation. And next, what we're going to do is try to formulate a dust model that can be used, or have a formulation that can be used by all ESMs. And we're also going to look at the influence of the vegetation and how vegetation influences in the cycle. Thank you.
Thank you, Yves. So the experiments that you ran there, when you said no dust, is that, as the reference, is that correct? Or it was rather you modified the treatment of the mineralogy and the size distribution between the two experiments?
Oh, we shut off the dust sources completely.
Okay, so you shut it off completely in the experiments.
Yes.
Okay. And just to follow up, so you were looking at an area of the Sahel, but the Sahara itself, well, it may not produce dust, but it produces a lot of sand, presumably, which one would classify as dust. So is there a need to consider better the treatment of production over the Sahara itself?
In terms of the
in terms of dust, yeah.
We haven't looked at the feedback at the emission. We should look into this to see if we improve. There have been considerable progress on constraining the dust cycle by the work of Jasper Koch, and there are two papers, one in 2017 and one in 2021 that's being discussed in ACP that's going to be published, that's constrained with observations and models the dust cycle over regions, and that's a considerable improvement to what we knew before.
Okay, so next round of Crescendo could benefit from such examples then, yeah. Okay, many thanks. We're going to move on. And next, if you could stop sharing, please, and if Dirk could start sharing.
Yes, I'll try to share my screen. Can you see my screen?
Yeah, that looks fine, Dirk. Okay, off you go.
Okay, so I will talk about the description of marine aerosol in ESMs and the impact on radiative forcing. So we consider as marine aerosol sea salt emitted from the ocean, primary organic matter, and DMS, which can be converted into sulfate. There are other non-marine aerosols like mineral dust, BVOCs, fire emissions. And in general, natural aerosol is the prevailing aerosol on a global scale, but locally anthropogenic aerosol can be more important. And you can also see that, for example, in the aerosol optical depth from natural aerosol globally being more important than from anthropogenic. What's the role of marine aerosol? First of all, it has an impact on the radiative balance of the atmosphere. For example, DMS or sea salt have impacts like -1 watt per square meter. Marine aerosol can also play a role in climate feedback. So when climate warms or changes, these emissions can rise or diminish and have an impact on the forcing. Aerosols have also an impact on the size of the anthropogenic aerosol forcing. It plays a role in air quality. And so if you want to model it well, you have to look at different things like emission patterns, how it's transformed in the atmosphere, deposited, transported, and so on. So in my talk, I will, in the first part, discuss a little bit how it's described in ECMs and how they perform. And in the second part, a little bit on how, for example, effective radiative forcing from anthropogenic emissions can be impacted by the natural background. So we looked at 5 Earth system models, which I listed here, which all have a description of aerosols in the troposphere, but sometimes limited description of chemistry. DMS emissions are often described in these models like describing a climatology in the upper ocean of DMS, then having a flux parameterization, describing how it's transferred to the atmosphere. This is rather similar in most of the models. And for sea salt, for example, there are also A few different descriptions, but in general they are rather similar, and also the number of modes or bins used in these models to describe sea salt is rather similar. So we look at simulations from the period 2000 to 2014, both free running or nudged and with prescribed sea surface temperature. These are the simulations which have been done by those models, where we varied, for example, the emissions from present day to pre-industrial. These models, for example, differ already in, for example, the amount of DMS emitted, which can differ by a factor of 2. The amount of sea salt can vary by a factor 2 to 5. Lifetimes of these DMS, sea salt, and sulfate can vary. DMS has a reasonably constant lifetime between most of the models. Sea salt can vary already more, and also sulfate can vary between a lifetime of 2 to 6 days. Also, which part is dry deposited from aerosols can differ considerably in the models, and also the AOD can differ, although we see that if we take, like, for example, pre-industrial emissions, we have reasonably aerosol optical depth between 0.09 and 0.11 in all these models. These are emission fields for DMS, which vary considerably, although a few of them have really the same climatology for upper ocean DMS behind them. So wind climatology can be quite different in these models, or how the actual transfer is described. Also, sea salt emissions is quite different, but we see, however, that in regions with high winds, we have the highest emissions. Then I will show a few comparisons with observations. So the first comparison is with aerosol optical depth over the ocean for these 5 models, and for CNRM we have like 2 versions. And on the bottom I show the median of an intercomparison study done by Jonas Gliss, recently published, which gives the mean of his study, which is the mean of 14 models. And what we see is that, and red is an overestimation of the aerosol optical depth, blue is an underestimation, and we see in most of the models we have the same patterns, but none of them is doing as well as the AeroCom median. We see an underestimation in most of the tropics, in most of the models. UKSM, which as we saw had a larger aerosol optical depth, has in most of the globe an overestimation. Then I show some comparison with DMS observations at Amsterdam Island. In black we see the concentration, the seasonal cycle, and the little dots are all the daily measurements. And in red we see the models. And so, for example, IPSL is reasonably well representing the seasonal cycle. Other models are doing a little bit worse. What we also see is that the daily variation in these models, so the size of the whisker plots, is like almost the same as from the observations. So it means that we have a reasonably well daily variation in these models. Another observation is, for example, the sulfates, which is then generated from this DMS. How well is it represented in different locations over the world? We see, for example, that it's reasonably represented the order of magnitude and the seasonal cycle, although, for example, in purple, this is NORI-SM, which has a very large DMS emission, also shows an overestimation in sulfate. Finally, some observation comparisons for sea salt. Also there, I would say that we reasonably well in most of the models have the right amplitude from the concentrations. The red is the CNRM models, which had the highest sea salt emissions, so also the highest surface concentration. The green is IPSL, which had, for example, rather low emissions, but a long lifetime also leads to high concentrations at the surface for sea salt. Then I will move to the sensitivity experiments. So recently there have been studies which publish the anthropogenic forcing from different CMIP6 models, but there is maybe an impact from the aerosol background on the size of this anthropogenic forcing. And also there have been studies publishing results on the size of the effective radiative forcing from from natural aerosols, but also there we can ask, isn't there maybe an impact from what background has been used for these studies? For example, the anthropogenic background then, was it 1850 of present day? And can that have an impact on the size of these estimates? So we did some sensitivity studies with these models. Now we couldn't do like long simulations because it's very expensive to do all these perturbations. So we only looked at the year 2014, but we did quite some perturbations, scaling the emissions from different species by a factor of 0, 50%, or multiplying them by a factor of 2. What we first had to look at is the effective radiative forcing in these models reasonable? And we see quite some variation, but in general, I think it doesn't change. It's not more variable than what we see in general in the results of CMIP 6. And then what we also had to look is that we wanted to use the nudge simulations, because then we use only like 1 or 2 years of simulation, and we had to see, is it the same effective radiative forcing in the reference state? And you see then that nudge simulations give reasonable agreement with free running simulations. And so now, how sensitive is the effective radiative forcing, anthropogenic forcing to the background? So what we did is what I show here, for example, on the left figure, is how the top of the atmosphere imbalance changes if I scale the emissions of DMS. If I go to more emissions like doubling, then I will have like a negative impact on the top of the atmosphere radiation. If I go to smaller emissions, then I'll have like a positive impact. I do the same thing in a nowadays climate. And if I take the difference between them, then I get this curve. And it explains how the effective radiative forcing from the anthropogenic impact changes with the background of DMS emissions. And we can do similar perturbations for sea salt. And then you see, for example, that here it's the opposite. So so for DMS, if I lower my emissions, I get a more negative anthropogenic forcing. If for DMS I lower my emissions, I get a more positive impact from anthropogenic forcing. For organic matter from the ocean, there was almost no impact. So this is just for one model showing it in one graph. And then the last thing I wanted to show is that the doubling experiments from natural aerosol are also sensitive to the background. And for example, we did some experiments, and what you see, for example, is that the sensitivity we find, for example, for DMS in EC Earth in present day, it's considerably different if we do a doubling experiment in a pre-industrial climate. And for example, the CMIP 6 results, they are based for 1850, while we have to consider now that these results might considerably different if we do that with respect to a present-day climate. So my conclusion, so emission parameterizations for marine aerosol are quite similar in most of these models. However, the actual implementation and the link with temperature and with winds make that the final emission strength can be quite different. Also, the lifetime for these species is quite different in these models, and we have varying agreement with observations. If we look then to the impact of these sensitivity simulations, then we conclude that there is some interaction between the background you use to study, for example, the natural aerosols or the anthropogenic aerosols. Okay, that's what I wanted to tell. So.
Okay, thank you, Dirk. There's a quick question, a couple of questions just popped in. From Bill, can you explain why increasing sea salt background increases the anthropogenic forcing? Seems counterintuitive. Yeah,
what I don't have the real answer for that now, but I think that maybe the size of the aerosol, of the sea salt aerosol might play a role, and that maybe sea salt aerosols might be a sink for other natural aerosols which live in the background, and by having less sea salt aerosol, you have also less sink for this other natural particles, so there will be maybe netto remain more small particles, so making the indirect effect weaker. But yeah.
Tatiana asks, how do you decide how to scale emissions in your sensitivity runs? Is there any back calculations with respect to how the emissions could have changed due to variations in ocean processes?
No, at the moment we just scaled. We just scaled them like a factor of 2 or a factor of 0.5. I haven't taken into account what could be a realistic size or from internal variability or other variability, which could give a good estimate for a reasonable sized perturbation. So I haven't done that.
Okay, and I have a comment which becomes a question as well. So unless you've got specific runs from UKSM, our AMIT runs, because we have DMS fully prognostic in the model, our AMIT runs, we based the AMIT runs with DMS drawn from the historical simulation. So they were kind of predicted, but yeah. And I'm just wondering what you think, if in a general sense for AMIT runs, do you think it's better that groups do that, or that they use climatologies?
I think it's a good idea to use in the AMIT runs a climatology which is derived from your own fully coupled simulation. It's something that for CMIP6 we have also done in NORISM. Also for this study we still used an external climatology which was LANA, but I think if the AMIP simulations should have a more explanatory impact or explaining better the behavior of your model, I think it's better to take a climatology based on your own coupled model.
Oh, good. Well, that's what we did. So you agree with us then? That's
I think so, yes.
Okay. All right. Thank you, Dirk. We will move on to Philippe. Philippe, I believe, is there.
Yes. Do you hear?
And Philippe can share. Yes, I can hear you, Philippe. Yeah.
Okay. Do you see my screen?
Yes. If you want to put it into full mode. Perfect. Okay. It's in full mode and you're ready to go.
Thank you.
All yours.
Okay, so good morning. So I will present you a bit on analysis or some work that was done during the CRESCENDO project around the carbon cycle of the land part and with the IPSL model and the CMIP6 versions, and especially the Orchidea land surface model. What do we have tested? And I first thanks all the colleagues and mainly Patricia Cadul, who contributed to most of the plots here. So I will just try to compare 4 different versions of our Orchidea land surface model, just as a backup, the IPSL CM5, where there were no downregulation of photosynthesis CO2. The published CMIP6 run, which is called IPSL CM6P1 in the remaining, where basically we had put a surrogate of the full nitrogen cycle with a downregulation of the typical VC max as a function of CO2 using a paper from Sellers in '96. And which is a simple statistical downregulation of CO2. The more CO2 you have, the lower the VC-max goes. And we have realized that these published runs were actually too strong, especially at high CO2, and we tested a bit during CRESCENDO period a new downregulation with a slightly more complex formulation that I will explain just after. And we compare also at the end with a version, a process-based version with the nitrogen cycle that is inherited from the OCN originally and developed by Nicolas Vuchard. This IPSL CMIP6 type run is only underway, but I will show some results. So the first thing is we realized that in the IPSL CMIP6, our downregulation was too strong, especially with very high CO2. So we tested with an optimization approach. We tried to optimize the different parameters so that we basically try to mimic the same results as the phase experiment, typically a 30% increase of NPP with a doubling of CO2. And we also look at some laboratory in situ experiments where they tested the GPP over time and with more 2 times, 3 times CO2 and trying to adjust the parameters so that we still get after 3 times CO2 still an increase of CO2 but not a decrease, an increase of the GPP, sorry, but not a decrease as it was the case in the CMIP6 versions. So this lower right graph now shows you the GPP increase for up to 4 times CO2s with 1% CO2 per year. And for in black, the CMIP5 version, where you had a large increase of CO2, so large beta factors. In red, this is the published CMIP6 version that everyone is using, and in green, a new version that we are going also, in green, the published CMIP6 version, and in red, a new version that we will publish. So basically, if we look at the historical period, all these simulations for the land that I'm concentrating here, all these simulations are also meeting basically the data range from the GCP. And this is here the estimates published by Pierre Freienstein. So basically, we are within the range of the GCP. The large ensemble, the different gray colors corresponds to the different members, the 32 members published within CMIP6. And the red is our new simulation that we just realized with this new down regulation. So now if we go to compare the beta factor using a typical 1% CO2 increase up to 4% CO2, we compare using the Aurora paper and the estimate that Aurora made in his recent paper, comparing the different CMIP6 run. So basically, if we start by the bottom, the lower part of the figure, so we see that the green round, that is our IPSL CM6 model, has a relatively low fertilization or beta factor, so-called beta factor, carbon concentration feedback. But with the new down regulations, we increase it significantly, and we put as a star the previous IPSL CM5 versions. And if we look in the middle part of the plot, what is the split of these contributions to the CO2 uptake by the different ecosystems? And we see, as expected, that the tropical range, 30 north to 30 south, is dominating the increase of carbon uptake for a given CO2 increase. So basically, what is a bit slightly frightening, at least from us IPSL model, is by playing with one equations, we change significantly one crucial important point that is discussed a lot for the compatible CO2 emissions. So what we then move now, I will show a tiny bit some more realistic scenarios. I take here SSP5 8.5 scenario, where on the upper right graph, it shows the concentration CO2 path in this scenario, which is the orange curve. And in the central panel, this our two IPSL Earth System IPSL CM6 run. One which has been published, which is the red below, where we really have decreased a low fertilization effect, and at roughly year 2100, the land start to become a source of CO2. While with the new down regulation, it needs to go up to 2,200 to start to be a source, and not so much. So you can imagine from these two curves that the compatible CO2 emission will be very different between these two model runs. And of course, what is important is, so we are now with our nitrogen versions. And as I said, only the full ESM run is in production. So it's running right now. But so we have done some previous tests, some SSP's 8.5 run with this Orchidea nitrogen cycle version, but not within the ESM, but just keeping a fixed climate, so which is still not ideal, and in a standalone mode. So with that, we can still compare the beta factors at 200 at 2100 at the end of this century, and we see that the blue dots brings back the nitrogen versions close to what is published in CMIP6, a low beta factor around 0.3 global, a bit more. But when we look now the trajectory in the change in GPP, not the net flux here, but just a change in GPP for these three runs, we see various behaviors. And if in the global, the nitrogen version, the mechanistic nitrogen version is close to our new down regulation, but what we see is that over the tropics, basically this light blue curve, the nitrogen versions, has a large increase of GPP due to nitrogen fertilization, while for the boreal ecosystem, it is much smaller because these ecosystems are starving from nitrogen. So you have really a different and contrasted response between a more mechanistic approach based on the nitrogen cycle and its impact on the carbon cycle, or
2 minutes.
a simple statistical formulation. So from that, another very recent plot that Nicolas Vichard did is with this nitrogen version, he tested with one CO2 trajectory, SSP 8.5, different depositions and different fertilizations, and it changed quite significantly the beta factor calculated with this simple approach of a forced orchidea simulations over up to 2,100. So the range is quite large, even with this model, depending on the type of deposition and fertilization. I won't go into the details. Last but not least, so now we are with these nitrogen versions, and we would like to know, given that there is the parameters have not been a lot optimized so far, we tested at a phase site, two phase site, Oak Ridge and Duke, to optimize the model against the NPP data and the LAI data that are measured at these sites. So the main message here is that basically the observations here are on the left, which is the NPP ratio from elevated to ambient treatments. And basically, our prior estimates are too low for these ratios. And only when we optimize against both the ambient and the CO2 data, we succeed in the far right with the both optim, we succeed to meet these NPP ratio. So that means we need to optimize against these data, but of course there is only a few, and it's not possibly not enough to use only the phase data to further constraints the model. So in summary, the CO2 fertilization is still, I would believe, at least within the Orchidea and IPSL model for the land part, not robustly modeled. Using two statistical downregulation formulation can lead to very different beta factors. Using a process-based nitrogen factors is indeed decreasing compared to our compared to our SMHI versions, but there is still large uncertainty, and we still need to use isophase data, although it's way more complex because you may have also an increase of GPP or NPP, but still no more carbon storage because root exudates increase a lot. And I will end up saying, so within Crescendo, we improve hopefully substantially our Orchidea land surface model. So we are in a better place to start the next phase, ESM 2025 project. And we will have now the nitrogen cycle. And I haven't spoken about that, but the permafrost and the forest dynamics. Thank you.
Thanks, Philippe. There's a question from Victor. How plausible is the GPP increase in the tropics in the Orchidea version with nitrogen limitation?
How much? I don't have that by heart. So in the tropics with the nitrogen versions, it's yeah, there is a nearly 40. Yeah, it's not in percentage. It's around 40 petagrams of carbon over the century.
He asks how plausible is that?
How plausible? Sorry, I didn't. I'm not sure. It's difficult to judge. I have no incentive to know how much it should increase over the tropic. I think it's too much given other nutrient limitation and phosphorus over the tropics. Okay,
and one last question from Pierre. Do you have more confidence in the nitrogen version as more realistic than one down regulation equation, or is it just bringing many more unknown parameters?
I think it's a good question. I would say at least, I'm not sure I have more confidence. I say at least it opens, it allows to check more this parameterization against other observations. With only a statistical downregulation formulation, there's not much that you can evaluate, check, and validate. So at least it's opened a greater potential for evaluation and validation. And I feel it's the only way to go forward.
Yep, okay, thank you. Good answer, I think, as well. Okay, we'll have to move on to the final talk. So if you could stop sharing, Philippe. And if Klaus is there, if Klaus could share. Okay, and you may need to unmute yourself, Klaus.
Yes, hello.
Okay, off you go.
Yeah.
Yep, we can see. Fine.
Oh, great. Good morning. I still think I can say I will talk to you about Crescendo Diagnostics for ESMValTool. And as you can see, many people have contributed to diagnostics in ESMValTool from Crescendo. So we're very happy about that. ESMValTool version 2 has been released, and we'll hear more about that from Axel Auer and Valerio Peylin in session D. And overall, from Crescendo, we had contributions to over 30 recipes in the new version of ESMValTool. And here I just want to show you a few of the highlights of these diagnostics. There are many more diagnostics even from Crescendo, and of course beyond Crescendo, more diagnostics in ESMValTool. On the slides, I give a lot of references, citations. These generally refer to the original publications that have served as the model after which the ESMValTool version of that diagnostic has been built. And beyond that, all ESMValTool diagnostics are documented in the online documentation. So if you want to know more details or have a look at other diagnostics, have a look there, as well as to the 3 papers that have been released on this topic, all of which you will find in the bibliography at the end of the slides. Okay, with this, let's go to the diagnostics. I have ordered them in 3 parts. First, we'll talk about routine evaluation, and then all kinds of diagnostics for different realms, and at the end, new models. The purpose of the routine evaluation is to assess the performance of the models and to have continuity when we're comparing different generations of models and data sources. So we start with relatively standard plots. For example, here we have the global surface temperature for the scenarios for different parts of the CMIP5 model ensemble. And similarly, a closer look where the individual models can be seen. We also have this kind of plots for precipitation and of course other variables as well, where you can easily do the multi-model comparison. So I should say, generally when we look at these diagnostics, it's always possible to easily apply them to your own selection of models, whether that's a different generation of CMIP or your own models in your institutes. We also have diagnostics for the sea surface temperature that can be compared against observations as always. And these kind of comparative model performance plots that are very famous by Glacial, where you have for every variable its own row, and the models in the columns, and the colors mark comparison with observations. If you are interested in assessing the individual models' performance without referring so strongly to the other models, you can look at the single model performance indicators as published by Kleinen Kim. And of course, we are also looking at the equilibrium climate sensitivity that can be quickly calculated after the method proposed by Gregory. And similarly, we are looking at the transient climate response. If you are interested to hear more about how ESMValTool can be used to quantify the progress across different CMIP phases, I invite you to have a look at the talk by Lisa Bock on session D on Tuesday afternoon. With this, we come to the diagnostics in the different realms of the Earth system. First of all, we have some diagnostics for extreme events. Here we show the consecutive dry days as an example of the climate indicators that can be calculated easily. We also have diagnostics for the upper atmosphere. Here we're looking at the temperature biases of different models, seasonally resolved, together with the multimodal mean. And similarly, we can look at the multimodal mean of the winds in the upper atmosphere. Recently, and this is one particular addition from Crescendo as well, we have extended the coverage of diagnostics also to the land domain. Here we're looking at the land cover and the different fractions, bare soil fraction, crop fraction, grass fraction, shrub fraction, and tree fraction. In this case, for the MPI ESM model, but of course, again, this can be easily applied to other models. The carbon cycle is another focus. Here we are looking at the net biome productivity. And here we have analysis of the land carbon turnover time. This, along with way more details, as I understand it, will be presented also in the afternoon in session B by Sujan Corrada. Then we move to river runoff. So we're branching out there slowly into hydrology, where we're looking here at different important catchments and that are stirred by shapefiles. So in this sense, if you are interested in similar diagnostics, but want to use different catchments or different areas, that is also relatively easily possible. Another big part has been the development of ocean diagnostics and ocean biogeochemistry. Here we're looking at the surface flux of CO2, comparing the newly integrated observational data set from Landschützer 2016 with several CMIP6 models. Likewise, the sea ice has seen more diagnostics added to ESMValTool. In this case, we're looking at the Arctic sea ice extent in September over many years, looking at both the individual models and the multimodal mean together with its standard deviation. And we see the analysis as well of the year of disappearance of sea ice in the Arctic. With this, I'm moving already to the last part of the diagnostics, which concerns emergent constraints. Here we're looking at a particular relation of CO2 at point barrels with the CO2 in the atmosphere. And this is used then in further analysis to establish the emergent constraint. As for many of the pictures that I'm showing you here, there are sister plots that are also generated that drive the issue further. Staying with emergent constraints, we're looking at emergent constraints for the equilibrium climate sensitivity that of course has received a lot of attention in the CMIP6 data. This is kind of following the evolution here from an earlier paper from 2015, where it's analyzed against the metropospheric humidity asymmetry index through a paper by Peter Cox in 2018. And
2 minutes.
Yes, thanks, Hazel. And the comparison of CMIP5 and CMIP6 that has been published just last year by Manuel Schlund, who has also worked on applying machine learning techniques to constraining. And I believe we'll see more details about that in session E on Wednesday morning. And with this, I come to the end. We've seen that Crescendo has contributed many diagnostics to ESMValTool, spanning all of the Earth system, really, and both for routine evaluation, but also facilitating new science. And of course, ESMValTool continues to be in development, and new diagnostics are added all the time. We are now on a regular release cycle, releasing 3 versions of the tool per year. And with this, I come to the end. Thanks.
Okay, thank you, Klaus. There's a question from Jeremy. How are the diagnostics made available to other users? Are they being added to the ESMValTool distribution?
Yes, these are all part of the ESMValTool distribution. So if you install ESMValTool yourself by following the instructions on the web page, and again, we will see some more details about the tool as a whole and the installation, I think, from Axel and Valerio. You will get these diagnostics. But if you're already using Jasmine, you can also just make use of the shared installation there. For details about that, you can also ask Valerio. And other institutes have similar installations.
And I have a kind of question. So it's around if there's any areas that I think we knew it. Let's say at the start of Crescendo that ESMValTool was pretty weak on ocean biogeochemistry diagnostics. So there's been some effort to cover that space. Are there any big gaps still where, you know, a large piece of science is simply not covered?
I think we've made some progress with the ocean biogeochemistry, but also there we will continue to improve. Otherwise, it's a bit difficult for me to say. If you notice, as a domain expert, notice big gaps, let us know. Then we can work together on that. But I have the impression that overall we have a good coverage of the data as it is in CMIP6.
Okay, great. There's a couple of comments in the chat that you can have a look at. They're not questions, I don't think. I think they're just comments. So with that, I'm going to wrap up this session. Thank you to all the speakers for keeping on time. It worked out really well, and for being there and for being clear with the presentations. So we now have an hour break.